Hello, welcome again to a colored algebra video. Um, this might be kind of a long video, or I might break it up into multiple videos, but I want to talk about all sorts of things related to exponentials and natural logarithms. Um, so let's just start with talking about um, inverse functions themselves. Because that's what E and natural log are. And I want to talk about it just kind of briefly as a graph. So let me throw some axes on here. So e to the x looks something like this. Of course, it's famous for blowing up very quickly. And natural log is defined to be its inverse. These two functions are inverses. And there's lots of different ways to think about inverse functions. And when there's lots of ways to think about it, that you almost always know it's an important concept, as it is in algebra. We do inverses all the time. To undo multiplication, we divide. So a few different ways to think about inverses. The most important one, I think, is that they cancel each other, right? They're going to cancel. And that's why they're so useful in algebra. If you want to get rid of an e, you can use the natural log to get to cancel it. But another way, just graphically, is so they cancel, but they swap x's and y's. So the reason they cancel is because the input of this function, so this function turns an input into an output. Natural logs are going to just reverse that process, turn that output back into an input. So you kind of undo, again, they cancel. You're going input, output, output, input. You're back to where you started. So just an example of this. So for example, let's say we had the point, this is not a perfect point, but let's say the point 2,7 is on e to the x. Well, natural log is going to flip those, and it's going to turn it into 7,2, which let's just say is about right here. And this point and this point is a mirror image in a way, right? It's a mirror of if this line y equals x were a mirror, you'd flip, this point right onto this point. It's not a perfect drawing, but you kind of get the idea. And with that in mind, you can actually create the entire graph of natural log of x. It's going to look like this. It's going to be a mirror image of the green one if this dotted line were the mirror. And that's how actually all inverse functions work. So just to do another example of that, let's say I was to look at, let's say I was to look at x squared, just for positive values. So if I draw that same line in, what should happen is the inverse of this function is going to be the flip of the green graph over this red dotted line. And that's exactly what you find looks something like this, is, of course, square root x. And those are inverse functions too. So you'll always get this kind of mirror image behavior when you're talking about inverse functions, which I think is pretty cool. If we go back to these pictures, you can also look at these pictures, these graphs, and figure out the domain of these functions. And what is domain? So domain, if you remember, those are the inputs you're allowed to plug in for any function that you're looking at. And for e to the x is really nice you can basically type in anything. But you only get positive values out of it. So you can plug in negative values of x. You can plug in positive values of x, and either way you get a positive value in the end as an output. Well, natural log is just the opposite. So what are you allowed to plug in to, what are you allowed to plug into the natural log? Well, you cannot plug in a negative, right? There's nothing over here for this natural log graph. So negatives are not allowed, so you have to type in positive. So you can get positive or negative outputs, but for the input, for the domain, it has to be a positive number for natural log. So let's do some quick examples of that. So like, let's say we were asked to find the domain. Maybe the first problem is e to the negative x squared plus 2. Second problem is natural log of 1/2 x minus 7. Maybe there's a third problem that is natural log of 1 interesting. 1 over x minus 2 plus x. Okay, so how do you do these problems? Well, this first one's really nice. I just said that you can plug in anything to an exponential function, it's good. And that's what domain is. So this is going to be all real numbers because you can plug in anything. So the interesting questions really come when you talk about natural log. So for natural log, it's not all real numbers. We have to only plug in positive values to natural log. Even 0 doesn't work. So what we need is we're going to set what's in the natural log. This has to be strictly bigger than 0. And so if we solve this, which I think we can do pretty quickly here, sorry. Add 7 to both sides, and we get 1/2. X is bigger than 7. We multiply by 2. We're going to get x is bigger than 14. So this is the domain. We need x to be bigger than 14 for this function to work. Okay. So those first two problems, knocked them out of the park. This first one looks a little trickier. But the basis of it is the same. Let me actually maybe do a new page here. We're looking at natural log of 1 over x minus 2 plus x. And again, the idea of domain is we just want a value that you can plug in here so that the natural log works, and that's always going to be whatever you're putting into the natural log. In this case, it's 1 over x minus 2 plus x. You want that to be strictly bigger than 0. So if we can solve this inequality, we're pretty good for this problem. Okay, how do you solve this inequality? Well, what I like to do with these ones is clear the denominator. So I'm going to multiply by x minus 2. And what that's going to do is that's going to get rid of that denominator. And I got to do that to both sides. So luckily with the 0 on the other side, that's not going to be too bad. So we're going to distribute that. It's going to look like x minus 2 over x minus 2 plus x times x minus 2 is bigger than or equal to 0. Well, 0 times anything is still just 0. That's kind of nice. X minus 2 divided by x minus 2, this is just 1. That cancels to 1. So we got 1 plus, if I distribute this x, we'll get x squared minus 2x. is bigger than 0. And, oh, you know what? I think this is going to factor. If I rearrange this, right, so we get x squared minus 2x plus 1. That factors as x minus 1 times x minus 1. That's nice. Is bigger than 0. Wow, that's actually kind of cool because I did not know the problem was going to work out this way. This is x minus 1 squared is bigger than 0. Well, when is x minus 1 squared bigger than 0? Pause it and think about this. This is an interesting question. But I will tell you. The square, when you square a number, it's always bigger than 0. Unless x is actually equal to 1. So, you know, we're looking for the domain here. This is always going to be bigger than 0 unless, again, x is equal to 1. So basically the domain of this function is x is not equal to 1. Because that's the only time when you square it, it's not bigger than 0, because it's equal to 0. So yeah, that's kind of an unusual case. However, we're not quite done yet. So we solved what we needed to solve. So we solved this blue inequality, but there is well, actually, let me back up. You know, what we really found, I think, in all of this, let me back up. So I think I was a little hasty when I said the domain was x equals not equal to 1. So we do get x minus 1 squared is bigger than 0. I think all you really get from that is that x equals 1 is a critical point. Okay, well, what does that mean? Well, critical points, if you remember, are just these values you plug on the number line to kind of see if it works. And you can to see which region of the number line works. So we get x equals 1 is a critical point. There's actually a second critical point, though. So we solved this all, and we only got this critical point. But you'll automatically get a critical point from any vertical asymptote, which would be, in this case, coming from this x minus 2, would be x equals 2. So you get these two critical points, and I think at this point, you just got to go to a number line and see which ones work. I was thinking maybe it was everything except 1, but I think I was a little hasty there. So we have 1, we have 2. So we have 3 regions. We have basically 3 regions of the number line we want to test. I guess let's first start by plugging in x equals 0. So if we plug in x equals 0, so that would be like, so I'm talking about this region here, 0. You're going to get -1/2 plus 0 is -1/2. You can't take the natural log of a negative. That's the whole point of this domain stuff. So 0, you know, it turns out you're taking like the natural log of a negative, so that's not going to work. Okay. Another number we could plug in would be like 1.5 in this region. If you plug in 1.5, you're going to get 1 over -1/2, which is -2, plus 1.5 is -1/2 again. That's negative again, so that's not going to work. And finally, I think if you plug in something like 3, that is going to work. That's going to be 1/3 plus 3. Yeah, that works. So what do we have? It's just this. that was definitely a complicated one, but you can see, if all else fails, go to a number line. That is our go-to inequality technique. Okay. So the next part of this video, or actually the next few parts of this video, all have to do with solving equations. That's kind of the next thing I want to get to. Now that we've covered some other things about natural log and e to the x and other exponentials. But before I get to solving equations, I want to cover the exponential and logarithmic rules. So you might have seen these before, but they're going to be helpful when solving equations, these things, as we'll see. Okay. What are the exponential and log rules? We'll start with the exponential rules. Green there. And then we're going to also, in the same slide, cover log rules. Okay. So what are the exponential rules? Well, they involve things like what happens if you add inside the exponent. So here this plus, I'm considering it inside the function because it's inside the exponent. Or what happens when you subtract, or what happens when you multiply. Well, each of these, we have a rule for it. So this one is going to be equal to a dx times a to the y. So notice it turned plus into multiplication. But you also have to pay attention, and this is very, like you have to get really into the, you have to turn on your brain's detail-oriented mode, I guess. But you have to keep track of which one's inside the function, that's the plus in this case, and which one's outside the two functions. So notice there's two exponential functions, the times is outside both of them. So an inside plus turns into an outside multiplication. An inside subtraction turns into an outside division. And an inside multiplication turns into repeated exponents. So like an exponent on the outside. Okay, so those are the exponential rules. For log rules, log is the inverse of, logs are the inverses of exponents, right? Well, all the log rules are just the flipped around versions of the exponential rules. So here's what we got. We're going to get multiplication on the inside becomes addition on the outside. So in both cases, it's turning multiplication to addition, but is it on the inside of the function or the outside of the function? That gets flipped. For exponential, the plus is on the inside. For logs, the plus is on the outside. For exponential, the times is on the outside. The logs, the times is on the inside. So, yeah, and everything just gets flipped around. So, for the subtraction, it's division on the inside is subtraction on the outside. And same thing for this one. An exponent on the inside is going to turn into a multiplication on the outside. Oof. Okay, so those are your log rules. Um, so let's maybe jump to solving some logarithmic equations. So for a first example, look at this logarithmic equation. 1/2 log of 3 of x plus 3 is equal to 2. Okay, how do we solve this one? Well, the goal here, like any algebraic equation, we're trying to get at the x. So at some point, we're going to have to undo the logarithm. And that's where we need the inverse function to logarithms, which are exponentials. So, but before I can do that, I kind of have to isolate the log. So let me first isolate the log by maybe multiplying both sides times 2. So I'm going to multiply this side times 2 and this side times 2. And we get, it's canceled, so we get log base 3 of x plus 3 is equal to 4. Okay, so what do we do at this point? Well, I need to undo the log to get at that x. To do that, I'm going to apply the 3 to the x function to both sides. So I'm going to apply 3 to the x to both sides. And this is what it looks like. It looks like I just kind of put a 3 like right here. What I'm doing is I'm taking a base of 3 and I'm raising it to the log base 3 of x plus 3. So that this whole thing right here, this is all now the exponent to this 3. And I have to do the same thing on the other side. So I take 3 to the 4th power. When I do that, this 3 cancels with that 3. I love it when things cancel in algebra. And of course, I've done that just specifically so the log would go away. So on this side, I'm left with x plus 3. And on the other side, I just have to compute 3 to the 4, which is 81. And so I basically got this solved. Now, it's always a good idea to check your answer on logarithmic equations because they tend to have extraneous solutions. This one I don't think does, but this will work. But always a good idea to check your answer. Let's do another one of these. A little harder. So we've got this one. Log base 2 of x plus 3 plus the log base 2 of x minus 5 is equal to 7. How do we do that? Well, the problem with this one is you have 2 logarithms, and they're not the same. You can't like combine them with like terms, for example. You know, as a first stab, you might want to do something like this. You might want to undo the log base 2. You might want to apply the x function to both sides, and we will do that. So you might do something like this. And you might think, well, I can just, you know, this is going to cancel those 2, so you're going to be left with x plus 3 plus x minus 5 is equal to 2 to the 7th. Well, you can't do that, though, because the 2 only is going to cancel a log if they're like right next to each other. But these logs are applying, and then they're added. So the adding is actually what is the main thing going on. You can't undo that with a 2. Okay, so what does that mean? Let me undo all of that. That was wrong. What do we do instead? Well, I said we couldn't combine these like terms, and that's true, but we can combine these logs. Let's see if, can we go back to our log rules? So the log rules work actually either way. So what we have is something that looks kind of like this, right? We're adding two logs. We can actually turn this into a multiplication problem like this. We're going to turn this into log base 2. So there's only one log now, but now it's multiplication of x plus 3 and x minus 5. And that's still equal to 7. Now that and this was using the log rule. Now that I've combined them, now I can do that thing that I was trying to do in red before, which is apply the 2 to the x function to both sides, like this. Now this is going to cancel, and I'm left with x plus 3, x minus 5 is equal to 2 to the 7th, which is what is 2 to the 7th? So 2 to the 5th is 32, 2 to the 6th is 64, so this must be 128. There you go. And now what we have, so we have this, we're not done yet, but we have this equation to solve. This is just a polynomial, right? You don't have to solve things like this. To get this working here, let me maybe FOIL this out. We're going to get x squared minus 5x plus 3x. That's going to be a minus 2x minus 15 is equal to 128. Okay. Having some lighting trouble. Sorry, I'm a little darker now. But let's keep going. Rain or shine, the show must go on. Let me add. Oh no, that's not what I want to do. I want to subtract that 128 so that I can maybe try foiling this. I'm sorry, try factoring this. I've got now x squared minus 2x. Negative 15 minus 128 is going to be minus 143. Oof. 143. Don't know how many of you learned your multiplication tables all the way out past 12, but I happen to know that 143 is 13 times 11. So I think if I make it a minus 13 and a plus 11, that should work out. You might not. You might have needed to work a little bit harder. You might not recognize that 143 is 11 times 13, but there you go. So we get two solutions here. We get two solutions of x equals 13 and x equals negative 11. And that's great. Remember what I said about checking your answer with logs? You gotta do that here. The negative 11 doesn't work. And I don't even need a calculator to see that. So if you plug in negative 11, what are you gonna get? You don't even have to take negative 11 plus 3. Not that that's hard, but I know that's going to be the log of a negative. And we just got done saying you can't take the log of a negative. That's outside the domain. So this is not going to work. And I think if you try 13, that does work. So that's your only solution, x equals 13. Okay. That's actually all the log ones I want to do. To finish this video up, I want to do some exponential ones. using a method called substitution. So we've already seen how to solve exponentials a little bit, but let me use a method of substitution. So like to solve this one, for example. 3 to the x plus 2 plus 3 to the x minus 1 is equal to 2106. Okay. How do you solve this? Well, I mean, my first thought would be to do it kind of like we just did, which is to use how we used the log rule to combine them. This kind of seems similar, right? We have two exponentials. Couldn't we use an exponential rule to combine these? Well, unfortunately, no. If you go back to the exponential rules, the plus has to be inside the exponent to use the exponential rules. There's no rule with a plus on the outside of the exponent. So the end result is we can't use a rule to combine these. Okay, so I'm going to use substitution. And I'm going to use the substitution y is equal to 3x. Okay. Okay, so how does this work? So you want to replace 3 to the x in your original equation with y. Problem, there are no 3 to the x's, just plain 3 to the x's in our equation. So what do we do? Well, we couldn't use exponential rules on this plus. Well, we do have exponential rules for this plus, this minus. What are those? Let me use some exponential rules here. So this becomes 3 to the x times, so the plus becomes a times 3 squared. Okay, still have this plus right here. This one is going to turn into a 3 to the x divided by 3 to the 1. So the subtraction becomes division. Okay? So that was exponential rules. Now I can use that substitution. So now I can replace the 3x with y like this. This is going to be y times 3 squared plus y over 3 to the 1 is equal to 2106. And there you go. That is how the substitution works. And I mean, we're not done yet. But now there's no exponential functions in this equation. This is actually, and it's actually even better, it's a linear equation. It's just, y to the 1, y to the 1. So I know we have some kind of big numbers and some fractions, but it's just a linear equation. We know how to solve this. Let me take it one more step, and I might take it to a new slide. So 3 squared is just 9. So this is just 9y, right? And 3 to the 1 is just 3. So let me actually bring that out as a 1/3 y. And now you might even recognize it more as a linear equation. I'm gonna have to go to a new slide here, but let me rewrite what we had. So we have 9y plus 1/3 y. What is that equal to? 2106. So, yeah, there's a few ways of solving this. I think maybe the way I'm going to go with is, let's just combine this, just use like terms. So this is just 9 1/3 y times y. So think of that as a mixed number. 9 1/3 times y is equal to 2106. 6. So let's just divide by that. 9 1/3. And we have y is equal to need a calculator. I actually don't have a calculator. So it's whatever it works out to be, some ginormous number, I guess. Well, I guess not huge because we're dividing. But yeah, whatever that is. Do I have an idea of what that's supposed to be? Oh, I guess it should be. I think it's supposed to be 243. Okay. So sorry, I did not have my calculator. I hope that's what it's supposed to be. Apologize if this video turns out to be wrong at this point, but anyway, you get some number there. And that's your solution for y. That's great. But remember with these substitution ones, you're not done. Because we don't really want to know y, we want to know x. Remember, y is equal to, remember what y is equal to? Y was equal to 3 to the x. So we want to really find what x is. Okay, so we're really solving the equation now. 3 to the x is equal to 243. How do you solve that? Well, it's an exponential function. And we know exponentials and logs are inverses. So we need a log. And not just any log, we need a log base 3. So if I apply the log base 3 to both sides, those are going to cancel. Log base 3 of 243, that's a calculator problem. So that was on a homework earlier to how to compute things like that. I think the way it works out is x is equal to 5. And so there you go. That would be the final answer for that one. Let's do one more substitution, since these are pretty difficult. Couldn't hurt to see one more example. So the other example I have here is 2 to the 2x minus 400 times 2 to the negative x is equal to 231. How do we do this one? Let's use the method of substitution again. All my U's look like C's when I write on the smartboard. There you go. Let's use the method of substitution again, and I'm just going to let y is equal to the x, even though I know there's no to the x. It just letting it be the kind of the basic exponential function, I think, is the way to go with these. Okay, so what do how can I make this substitution work? Well, once again, we have exponential rules for these things that can help. So this one, if, we can't substitute in y yet, but if I rewrite this, using the fact that it's a multiplication on the outside, turn that into a repeated exponent to the x squared, then I'm going to be able to make my substitution with y here in a second. Okay, what about this 2 to the negative x? Well, I didn't actually write that rule, but you can think of this as you can derive this rule from the subtraction rule. A to the negative x is just 1 over a to the x. So that's what we're going to do with that one. So this is going to become minus 400 to the negative x using this rule would be 1 over to the x. And so, I guess that equals 231. And so now I can do that, my substitution. This is going to be y squared minus 400, 1 over y is equal to 231. And once again, I've gotten rid of my exponential function. So now I'm solving a type of problem I kind of already know how to solve. And this is not an easy one by any means, but in theory, we can solve something like this. Let me take this one step further. Let me multiply both sides by y. I'm going to clear the denominator. And what you're going to get is forgot to multiply this side by y. So we multiply both sides by y. We're going to get y cubed when I distribute this y in. These y's cancel. So I get y cubed minus 400 is equal to 231y. Okay? So let me go to another page. So I get y cubed minus 400 is equal to 231y. All right. That looks tough to solve, but let's give it a try. So we're going to subtract the 231y over. Equals 0. Yikes. What's going to solve this one? Well, let's, we've got a lot of factors here. So we might use the PQ method. We've got a lot of factors of negative 400 to try. But, you know, it seems reasonable that we're kind of looking maybe for some positive solutions. And if we're looking for a positive solution, it's going to have to be pretty big, right? It's like 2 is not going to work. It's going to be way too negative. But something really big. So 400 is another possibility. But 400 cubed is gigantic, so that's kind of too big. So it has to be kind of in the middle. I'm gonna use some. I kind of know because I created the problem. I'm gonna guess that maybe y equals 16 is gonna work here. Let's actually try that with synthetic division. So we're gonna put the coefficients 1, 0, negative 231, and negative 400. And so we get 1, 16. 16 times 16 is 256, I happen to know. So you subtract those, you're going to get 25. And 16 times 25 is 400. Oof, amazing how that works out. So we're going to get this as our factorization: y minus 16 and y plus 16, y squared plus 16, y plus 25 equals 0. So that's not going to factor because your only factors are 1 and 25 and 5 and 5. Those are going to add up to 16. So your solution, they're going to come from the quadratic formula. So we get solutions of y is equal to 16 and let me maybe squeeze it in over here. So if we do the quadratic formula, it's going to be negative 16 plus or minus the square root of 16 squared minus 1 times 4 times 25 all over 2. So it's going to be negative 16. Again, 16 squared is 256. I happen to know. Minus 100 would be 156. Plus or minus the square root of 156 over 2. Okay, so all of this is great. We've got some solutions here, but these are all solutions for y. Remember, we need to get solutions for x. Well, how do we do that? Remember, this was on the previous page, I guess, but y is equal to the x. So we need to solve to the x. So from here, we need to solve to the x is equal to 16. And from here, we need to solve, to the x is equal to all this stuff. Well, something that's kind of nice, I noticed that these are negative, right? Because the root 156 is going to be smaller than negative 16. So, when we're solving something like this, to the x equals a negative, you might be tempted to, okay, let's take the log base 2 of both sides. But automatically, even though you don't know exactly what this number is, because you know it's negative, you know this is not going to work. Again, what's the domain of natural log? Or sorry, what's the domain of logarithms? Must be bigger than 0. So you don't actually get any solutions out of this. That was all, I guess that was all just an exercise in futility. But you do get a solution from this one. So if I apply the log base 2 to both sides, that cancels that. So I get x is equal to the log base 2 of 16, which you might recognize as being equal to 4. So that is my final solution on that one. Okay, thanks for your attention and have a great day.